Hello, everyone. Welcome to the MIF++ seminar. Today, Ritchie will talk about exploiting powder X-ray diffraction techniques for automated phase isolation in the laboratory. Please, Danny.
Hi, thank you for the introduction. So yeah, this is the project that I've been working on. Turned out to be a very exciting project. It's moved along quite rapidly, and I've quickly started working with experimental people in helping them with their tasks. So a lot of it has been done very quickly, and I'm basically at the point now where I'm looking to publish a paper, but I would be targeting a chemistry journal, and so much of the stuff I've done, which is about sort of probabilistic methods in affine geometric spaces, wouldn't really be suitable for that paper. So I just wanted to give this talk about the maths that I have done and to see if people are interested in it and if they feel it's worthy of looking into further or developing. So I'll start. So first I'll give a problem statement and a general outline of my solution. And then I'm going to go through the construction of phase space P, which is a mathematical representation of chemically allowed compositions, and then go through my solution to the problem with no experimental error, and then how I use a probabilistic method to account for experimental uncertainty. So firstly, some chemistry definitions. A word of warning, I think some chemists might disagree with how I'm using these terms, but it allows me to be far more concise with what I want to say to you, and it sort of incorporates some of the assumptions that I've made, just to make it all a bit clearer. So, a phase field is a set of elements with fixed ionization states, so a single ionization state for each element in the phase field. Composition in a phase field is an amount with each element. A phase in a phase field is a composition that, at thermodynamic equilibrium, forms a single crystal structure. So, in general, an arbitrary composition, when it reaches thermodynamic equilibrium, will decompose into a set of phases. An amount of each as well, a ratio. And importantly, the weighted average of the composition of these phases will be the initial composition.
Danny, could I ask a quick question on the previous slide? So you said a phase should form a single crystal structure. Is it possible that one phase forms more than one crystal structure?
Yeah, so these are known as polymorphs. I think the basic example is pure carbon, can be diamond or graphite. Mm-hmm. In the work I've done, I'm assuming that this isn't the case. It's not like breaking my thing if it does form multiple crystal structures of that exact composition. But for the work I'm presenting, we're assuming that a phase is a composition which forms a single crystal structure.
Will it be really important that it is a single one, or could it be more than one?
What's important is that even if it forms multiple crystal structures, all of those crystal structures have the same composition, which is that composition. That's the important thing, and that is true.
Okay, so possibly saying forms at least one crystal structure doesn't change really anything later.
Yeah.
Mm-hmm. Okay, thank you, Danny.
Oh yeah, so please feel free to ask any questions at any point. So the experimental analysis for the data which I've been using is powder X-ray diffraction. For me, this means it's an experimental technique for analyzing compositions after they have reached thermodynamic equilibrium. Known phases are defined as phases which have a mapping from their PXRD signal to their composition. So a database exists, and if that known phase is present in a sample, then the PXRD will identify that, it will know its composition, and additionally, it can estimate the relative ratio of multiple known phases in an input composition. On the other hand, unknown phases are those for which the mapping does not exist. PXRD will still be able to tell you that there's an unknown phase present, but it will not know its composition, and it will not be able to estimate its relative ratio to any of the known phases. This allows me to say my problem statement quite concisely. So PXRD of an input composition has identified some known phases and a single unknown phase. What is the composition of the unknown phase? To do this, first, I'm going to calculate the average composition of the known phases. And then I'm going to use the fact that the input composition will be a weighted average of the unknown phase and the average composition of the known phases. So before we get into that, I need to go through my construction of P, which is my mathematical representation for chemically feasible compositions. So first of all, we need to talk about what it means for a composition to be chemically feasible. And there's basically 3 rules. Number 1, the composition must be charge neutral. Number 2, compositions with equal ratios of elements are equivalent. And number 3, the amount of each element in a composition must be greater than or equal to 0. So consider the phase field for O elements, label them with I. Any composition C can be represented as a Euclidean vector in RO, where the ith component gives the number of moles for the ith element. With Qi as the formal charge for the ith element, as you remember, we're assuming each element has only a single ionization state, so Qi is fixed. Then the charge neutrality constraint implies that the sum of Qi equals 0. And then
Danny, a quick question on notations. Since you are still in the writing phase, I guess, right? So you are writing a paper, right? Not yet finished. So I'm wondering, so this notation small o, which might easily appear in the same equation with 0.
Yeah, that now that you say that, it is a bit of an oversight. I just picked it because it's the letter after N.
Oh, I see. Well, how about M, which is right before N?
Yeah, but M, you've got like masses and...
Okay, fine.
Yeah, no, there'll be a different letter I can use. Okay,
great.
Thank you for the input. We quickly swap to N, don't worry. So because compositions with equal ratios of elements are equivalent, C can always be chosen so that the sum of Xi equals 1. So we have 2 independent linear equations. They will each constrain C to lie on an O-1 dimensional hyperplane embedded in RO, and therefore an N equals O-2 dimensional hyperplane can be found, which any C will belong to. I call this hyperplane P. A basis for P is easily found by taking the normal vectors for each of the O-1 dimensional hyperplanes and then finding n orthonormal vectors which are orthogonal to both of those normal vectors. And then these vectors will form the columns of B, which is our change of basis matrix. In order to consistently represent compositions in P, it's necessary to choose a fixed composition, A, and then we say that the representation for C in P is defined by this equation here, which is basically its representation in the constrained space, but relative to A. The condition that the amount of each element in a composition must be greater than or equal to 0 basically translates to a set of linear equations which will form our bounds on P. As you can see here, this is the phase field for the lithium boron oxygen bromine space. So this is an example of one orthogonal set of basis vectors you can choose. We had 4 elements, so we're working in a 2-dimensional space. We have 2 basis vectors. Each one of these vectors will lie in the original 4-dimensional space, but you can express all chemically feasible compositions inside this space. And as you can see, for example, setting lithium equals to 0 translates to this line here, and etc., for all the other elements. That's my construction of P. Any questions at this point before I move on to the next stuff? Okay, great. So the solution, assuming no experimental error, is quite simple. So let F in P be the sampled composition. So that would be this purple cross here. For each of the known phases, Ki, this is the orange dot, the blue dot, and the green dot, PXRD analysis can determine their relative abundance, Wi. And this allows us to work out the average composition, K tilde. K tilde is shown here as the green cross. This is useful because now we can represent S as a weighted average of the unknown phase, the blue cross, and the average composition of known phases, the green cross. As you can see, these 3 points are collinear. This equation can then be rearranged to show that U will lie on the line segment starting at the sampled composition, moving away from the average composition of known phases until it reaches the end of space.
Danny, quick question. So you are quickly moving to this deep mathematics, but before we go into technical details, so probably this slide is most important for understanding how PXRD is used, right? Yeah.
So PXRD, the red dot was assumed to be the unknown phase. So PXRD identified that there was a red dot there, but didn't know its composition and didn't know its relative abundance to anything else. So the task is to find where the red dot is. It could see, however, the presence of the orange dot, the blue dot, and the green dot, and it knew their compositions. It knew where they lie in composition space, P. And it can also estimate the relative ratios between them. These are the Wi. Because you have these relative ratios, you can then take a weighted average of these 3 points using the relative ratios to calculate the average composition of the known phases, which is this green cross here.
Danny, could I check? So when you say unknown phase, this is a randomly sampled chemical composition or something else?
The purple cross was a randomly sampled chemical composition. The unknown phase was something that was present once that composition reached thermodynamic equilibrium. In reality, we wouldn't know its composition. I wouldn't know where to plot this red point on the diagram, but because this is looking at past experimental data, I do actually know where it is.
Okay, so practically in the lab, we take a composition at this purple cross.
Exactly.
And then if an experiment is successful, or actually, or not, what happens?
We're assuming cases where in the lab, they've taken the composition at the purple cross, they've let it reach thermodynamic equilibrium, and then they've analyzed it using PXRD techniques.
Okay.
The analysis has shown that there were some known phases, these 3 dots, and one new unknown phase, the red dot.
Only one unknown.
Only one unknown.
But we don't know the position of the red dot. Yet.
Exactly.
But we know 3 other dots.
Yes.
Well, so this seems a very powerful technique then, because we give to PXRD really something unknown, and it decomposes into, say, 3 knowns, as in this case, and 1 unknown.
Yeah.
Yeah, I'm not an expert in PXRD, but so is it really the case? Is it?
Yeah, these sort of methods have been used for a long time. They will trial a new composition. It will come up with something new and some things that they know about, and then they try new compositions which are further away element-wise from the known things that they formed, in the hope that they form a higher amount of the new thing. And they use this sort of trial and error approach to locate the unknown thing. However, it doesn't really scale well as you go up in dimensions. So this is more of a systematic way of using that process.
Okay. Maybe one more question. So S here, S denotes the purple cross, right?
Mm-hmm.
Okay, yeah, please continue with your explanations. Thank you.
So, assuming no experimental error, because of the weight fractions returned from the PXRD analysis, we know that the new phase, the unknown phase, will lie somewhere on this blue line. Unfortunately, there is lots of experimental error, and the weight fractions are not accurate. So rather than representing K tilde, the average composition of known phases, as a single point, I use a random variable, which is a multivariate normal distribution, such that I denote that distribution K, such that Fkx gives the probability density of the composition X being the actual average composition of the known crystals.
So I have a question. Obviously, this part is important. Same way, is there this
Sorry, I don't know. Is the audio for Larry working?
No, sorry, that completely dropped out for me.
Yeah, let's wait a bit.
No.
Larry, I didn't quite catch what you said. I think your audio is lagging a bit. Maybe the internet's not working properly.
Yeah,
It's an internet problem. My question is, how does experimental
Larry, one more option is to type your question in the chat briefly, at least. Could you let us know if chat is accessible to you? So sometimes, so it's not always working. Just in case, I'll make you a co-host, and then hopefully chat should be working for you. Okay, I hope what Larry is typing. Danny, would you like to simply explain this current slide without moving quickly ahead? That's the question. So does the experimental error in measuring the intensities enter the same way?
Does the experimental error in measuring the intensities enter the same way? I'm not quite sure what you mean by that question, I'm afraid. The experimental error is associated with the estimated relative weight fractions, Wi. If you mean by the same way as in I'm not sure.
Okay, if I understood correctly, you modeled Danny.
Exactly, it's the same. Yeah, it's the same uncertainty. So the measurement of the PXRD intensities is exactly the error associated with the Wi. That is the error. Does that answer your question?
Let's try this again.
Sorry, I still can't hear your audio. Okay, thank you. I'll continue on. So we introduce this multivariate normal distribution such that fkx gives the probability density of the composition x being the true average composition. So here, I mean, obviously, the normal distribution's support will actually be the entirety of P, but I've just drawn the support for like 99% of probability mass or whatever. So here's P, just a square box. Here's the sample point, and here's the distribution where we think the average composition is going to be.
Sorry, Danny, I know we talked about this the other day, but something's just occurred to me. So when you say that the support is the whole box, I mean, to be clear, it's not in the sense that the support is the entirety of this hyperplane.
The box is the entirety of a hyperplane.
So this box is not, when you're representing the box here, it's not the one bounded by the composition restraints.
The whole hyperplane is bounded by the composition restraints.
Oh, I see what you mean. Sorry. Yes. All right. I think I see what you mean. Yeah.
Yeah, I think it would be difficult to find a phase field where the bounds on P end up being so nicely orthogonal, but this is just to allow me to talk about it. So here we have our sample point. Here we have our distribution for where the average composition of known phases could be, and the box is our P, our phase field. So what I want to do is, first of all, calculate the probability density that U belongs to this line segment, LSK. So if U is in this line segment, LSK, well, I should say it the other way around first, my apologies. Let's assume that this point here, K, is the average composition of known crystals. This would mean that the new unknown phase would lie somewhere in this line segment, LSK. However, LSK is not unique. If the average composition of known phases was K1, or if it was K2, the induced LSK is the same line segment. So to calculate the probability density that the unknown phase lies in the line segment LSK, we need to integrate the probability density over the entirety of this line. We can describe this line just with an equivalence class on K, where K1 is equivalent to K2 if it can be reached by some vector from K to S. So we want to compute the integral over this equivalence class here to get the probability density that U lies in this line segment LSK. In order to do this, the first step is to take the marginal distribution of K on the orthogonal complement to S minus K. In this case, it's just a green line, but in general, it will be an n-1 dimensional hyperplane. In order to do this, we construct A, which is a matrix which maps from P to the orthogonal complement. And then the marginal distribution of K is simply given by the transformation of the mean and covariance matrix as shown. The next step, we want to find this point of intersection between the line S minus K and the orthogonal complement. This is simply A transpose S, as A will project S onto that intersection point. So denoting that intersection point Y perp, then this will allow us to compute FLSK, the probability that the new phase will lie on the line segment LSK, as simply the probability density of the marginal distribution at the point Y perp. The final step is calculating the probability density of the unknown phase being a point belonging to that line. and that is simply the probability density of it lying in the line divided by the Euclidean length of the line. I can stop there for any questions. That's the core. Oh, pretty picture. This is the multivariate normal distribution for where we think the average composition of known phases is, and then this is the corresponding distribution induced, which gives the probability density for the unknown phase being at any particular point.
Daniel, this particular picture is two-dimensional, right?
Yes.
Mm-hmm.
So I chose 4 elements so that the constrained composition space was 2-dimensional so that I could make pictures. But in general, this method works for arbitrary dimensions.
And the composition of 4 elements is already realistic. So it will be helpful for experimentalists, right?
Yeah, I'm currently working with someone doing 4 elements, 5 elements, and 6 elements.
Mm-hmm. And when this picture will be 2-dimensional, 3-dimensional, or 4-dimensional?
Yeah, I haven't done the 4-dimensional picture. I haven't worked it out yet.
Okay. Okay. So indeed, any questions at this point? Okay, then yeah, feel free to continue, Daniel.
So a quick word about combining distributions from multiple sampled points. So each time you sample a composition, to get it to reach thermodynamic equilibrium and then do the PXRD measurements, then you get this cone basically. And so if you do multiple sample points, you can simply combine that information by multiplying the probability distributions together. However, when I'm calculating the distribution over a discretized grid, the discretization scheme I use is unique to each sampled point. This is because I can greatly reduce the computational complexity. As I've gone through here, each point X belonging to the line LSK will have the same probability density. And so I initially discretize P into a set of lines LSK, and then I discretize each of those lines into a set of points. But the disadvantage of that is that it means the discretization scheme will be different for each sampled point. The way I'm currently getting around that is simply using a linear nearest neighbor. Yeah, a nearest neighbor interpolation to recompute the probability density over an orthogonal grid spanning P. But the question for whether this is the most suitable way to combine probability densities defined on different discretizations of the same support is still open for my work. And then a quick bit about how I choose the parameters of multivariate normal distribution. Naturally, mu is set to k tilde, the average composition of known phases that we calculate. For the covariance matrix, so we're associating an uncertainty with each of the weight fractions returned from the PXRD analysis. Usual error propagation techniques can be employed to then obtain the standard deviation on each of the elemental amounts. So if we're picturing our k tilde in the original RO dimensional space, then if you remember, each of the components of that vector will correspond to an amount of each element, and we have an associated standard deviation for that amount of that element. Now, assuming that these standard deviations are independent, then an O-dimensional square covariance matrix can be constructed by placing, well, the variances, the standard deviation squared along the diagonal of that matrix. And then this is easily projected onto the hyperplane P just by transforming it with the change of basis matrix B, which I defined earlier. More experimental data is required to optimize the choice of the standard deviations associated with WI, but from the experimental data I do have, I've been able to establish like a rough order of magnitude of what works. Now I'm going to show you some results. This is from experimental data kindly provided by Yung Dang, who's a postdoctoral researcher in Matthew Rosinski's group working at the Materials Innovation Factory in Liverpool. So it's the same phase field. All these pictures are the same: lithium, boron, oxygen, bromine. For each of these pictures, you can see the sampled point as the blue cross, the average composition of known phases as the orange dot, and in general, you wouldn't actually know where the new composition is, but because this is past experimental data and Yung did go on to identify the composition of the unknown phase, then I've also shown it plotted here as the green cross. So the idea is we're trying to find the green cross, and here's our probability distributions for it. So as you can see, some of them are accurate, some of them are less accurate, but these are all okay. The issue was there were three of them were really bad. This posed a big issue for me because when I merged my probability distributions by taking their product, then they were zero everywhere. There was no overlap, and that is obviously not ideal. So I had a little think about how I could get around this. This was a very quick solution. I was actually surprised by how well it works. To talk about it, I've tried to write it up in set theory, but I don't actually know any set theory, so I'm sure there's a way to write this more concisely, but I'll give it a go anyway. So if we define S as the set of all the probability densities from each of the sampled points, then that's S. Then if we define Ri as each member of Ri will be a combination of members of S of size n minus I. And in Ri, you'll have all possible combinations of that size. So each element of Ri is a combination of members of S. So as I just mentioned earlier, when we have I equals 0, i.e. Ri only consists of the full set S, then the probability density was 0 everywhere, which was an issue. So then, okay, how about when I equals 1? So we've got all possible sets of S where you're only leaving out one of the sampled points. Those were all still 0 everywhere. So basically I went through increasing I, making Ri bigger and bigger, and each element of Ri being of smaller and smaller size, until when I was looking at the merged probability distributions, at least 50% of them weren't 0 everywhere. I chose 50% arbitrarily. And then that allowed me to create this plot here. So I ended up with looking at combinations of size 7. So taking all combinations of probability densities of size 7, then selecting only those combinations for which the merged probability density was not 0 everywhere. Then I make this plot here. So on the x-axis, we've got each of our sampled points, which have been arbitrarily enumerated, and then it's showing the amount of times that sampled point occurred in one of the combinations that was not 0 everywhere. And it worked really well. As you can see, samples 6, 7, and 8 scored extremely lowly, and that was precisely these three. And then finally, I made a plot of the merged probability distribution excluding sample 6, 7, 8. And as you can see, pretty close to the goal. This is good. If you made this, you would have a high chance of forming a nice single crystal of this new phase, which would allow you to analyze it and make progress. Interestingly, this was also a great showcase for the versatility of my technique. I mean, there's some questions of like, you know, why bother using this like such a complicated method to construct a cone when really you could just perhaps bung any sort of roughly cone-shaped thing on. And, you know, it allows me to have elliptical cones and because of the complication of its construction. But I talked with Yung about why some of her samples might have had such a high error, and she actually only then told me that she did believe that they would have a really high error because she saw a lot of an amorphous phase in them. Amorphous phases are like glass, and basically they're an issue because they don't show up in PXRD. She said that the amorphous phase was likely to be B2O3, and she estimated that there was quite a bit of it. So what I then did was that for those samples 6, 7, and 8, I included a 70% ratio of the amorphous phase with a very high uncertainty on it, just to see what could happen. So here we have it with no change. These are all for the same sampled point. So I haven't added in the amorphous phase in this picture here. In this figure, I've added in the 70% of the amorphous phase, but I've assumed that 70% was accurate. The associated uncertainty on the 70% was still low. And you know, as you can see, this helps the cone is getting closer to the goal. But then naturally, what really helped was assuming quite a large uncertainty. It was like if the ratio was 70, it was like a plus or like 15% standard deviation. And then, as you can see, this having the high uncertainty only on the oxygen boron phase stretches the distribution in that way, which correspondingly stretches out the cone, and it's starting to look a lot more feasible. One potential problem with my method, which some of you might have picked up on, is that the support of K, as I mentioned, is in fact the entirety of P. And so the assumptions I have made are technically incorrect. So if you consider the green line segment L1, if this was in fact the average composition of known phases, then the new phase would be on the green line segment L1 prime. But my analysis doesn't account for that. My analysis would still assign that probability mass contained in this green line segment to the red line segment and assume it induces the new unknown phase to be on the line L2 prime. So this could be an issue, and basically what it comes down to is the relative probability masses in the green line in L1 versus L2. So in order to be confident that my results are valid, what I do is I keep track of the cumulative probability of S for the marginal of K on S minus K. So basically just looking at the probability mass of the red line and hoping that it's close to 1. And here's a plot of that. So I increase the predicted error on each weight fraction. The rough amount that I normally use is about like 0.2, so somewhere here. And then here you see the cumulative probability for the line segment up to S. So 1 is what we want. So as you can see, as the predicted error does increase, then we start to get a sign that the method I've used isn't appropriate. But I believe that while it's still essentially 1, then it's okay. Yeah, and that's it. So thank you very much for listening. And does anyone have any questions?
Yeah, I'm pretty sure there will be questions, so keep your slides. And okay, let us first thank Danny. By a round of applause, please. Okay, then I'm stopping recording.